Okay, so in this problem, again connected with Jordan forms, you know, Jordan forms really only get interesting when you get very large matrices. But of course, doing the arithmetic for very large matrices is very hard for us to do. And so I quite like this problem in that it enables us to analyse Jordan forms, but of a 12 by 12 matrix. And I don't tell you what the matrix is, and I don't care about the P matrix that sends it to Jordan form. But what I do is I give you some information about the dimensions of the null spaces. So I tell you the nullity of what happens when you take this massive 12 by 12 matrix that remains hidden, and I subtract 7i, and the nullity of the dimension of that kernel is 4. So by the way, and similarly, if I take a plus 3i, the dimension of that kernel is 2. So that's telling me immediately that lambda equals 7 and lambda equals minus 3 are eigenvalues for this matrix. And the question also tells you they're the only eigenvalues. So they're telling you what's happening, so that means there are 4 eigenvectors, 4 linearly independent eigenvectors for lambda equals 7, and there are 2 linearly independent eigenvectors for lambda equals minus 3. And this is telling me what happens when I go take the higher level kernels. So let me draw the onion diagram. In fact, there are different ways you can draw pictures for this. You can use a cross diagram or a block diagram, or you can use the onion. I'm going to use the onion here. I like the onion. So the innermost kernel of this one, that is if I look at the kernel of a minus 7i, that's got dimension 4. So that's got 4 eigenvectors. So I put 4 crosses in the innermost kernel. When I go to the next kernel out, that kernel now has dimension 6. So that means it was 4 in the innermost one. I've now got 6 generalised eigenvectors. So that means I pick up 2 more. And that's the only information I'm given about that. So at the moment I have 6 dimensions worth of generalised eigenspace. Now I'll do the same thing for lambda equals minus 3. So the innermost kernel telling me the eigenvectors, and I've got 2 of those. I go to the next kernel out, that's the kernel of a plus 3i squared, and the dimension bumps up now to 4, so I'm picking up 2 more generalised eigenvectors in the next kernel out. I go out to the next kernel again, that's the kernel of a plus 3i cubed, and this time I pick up, have total dimension 5, so I've got 2 plus 2 is 4, I need 1 more. Now at the moment then, how many dimensions of generalised eigenspace do I have? Well, I've got 6 at that point and 5 there, so I've got 11 dimensions worth of generalised eigenspace. But remember, I started with a 12 by 12 matrix. So there's 1 more dimension of eigenspace somewhere. And the question asks, what are the possible Jordan forms this matrix could have? So, what could we do? Well, one possibility is to do the following. That extra dimension of eigenspace might be in the lambda equals 7. So it might be the case that I go out 1 more kernel and I pick up 1 more generalised eigenvector. If that were the case, then I can write down what the Jordan form of this matrix is, because I can tell the size of the Jordan blocks from the chains. So I've got 1, 2, 3, 4 chains in that matrix. So possible Jordan form is I could have 1 chain of size 3, so that's a block of size 3 corresponding to lambda equals 7. Followed by a chain of length 2, so that's direct sum J2 based on 7. And then I've got 2 little 1 blocks. So that's plus J17 and that's plus J17. Then I can add in the blocks from over here. So this would have a block of length 3. So that would be a Jordan block of size 3 based on minus 3. And I should say, another 2 chain, which is a block of size 2 corresponding to minus 3. So that would be the Jordan form in that particular instance. Well, there was a little bit of choice there, so I might have had the following. I might in fact have had the extra the dimension of generalised eigenspace here, and that means I would have had my generalised eigenvector there. And in that case, then the Jordan form, this wouldn't be there anymore. I would just have two little 2 blocks. So I'd have J27 direct sum J27 and 2 1 blocks. So the direct sum J17 direct sum J17. And now for the lambda equals -3, I'd have a 4 chain there, giving me a 4 block over here. And then I would have a little 2 1 there. And they're the only possibilities I can have. So there are 2 possible Jordan forms of this matrix. So even though we don't know what the matrix looks like, the dimensions of the kernels, dimensions of the successive kernels that we get by taking powers of A minus lambda I, enabled us to pin down, at least to 2 possible cases, what the Jordan form might look like.